Bismillahirrahmanirrahim. Hello students, welcome to the next lecture of our fluid kinematics module. So today we are going to revise some of the concepts and introduce some new terminologies. So let's go ahead and define a system. That what do we mean by a system? So when I'm going to talk about a system, I mean a portion of fluid. By system, I mean a portion of my fluid. And you have heard this one in the previous lecture is what is control volume. So control volume is my fixed geometry, means a fixed shape. Okay, so by system I mean a portion of my fluid, because we are dealing with the fluid kinematics. So whenever I say a system, so I mean a portion of fluid, and by portion of fluids it means it is deformable. It can be deformed, it can flow, because we are dealing with fluid kinematics. And by control volume I means that my geometry is fixed. So in today's lecture we are going to develop a relation between our system and our control volume. So what does this mean? Because in our daily life we counter several such problems in which we are dealing with a system of fluid and control volume. So let's go through some practical examples, and then I'm going to come to my main topic. So let's suppose you have seen this example time and time again. There is a pipe, and I can say that there is a fluid flowing in this pipe. So in this case, the pipe is my control volume. Given that I'm studying the flow of the fluid inside this pipe, and here the fluid is my system. Okay, so if I'm concerned with the flow in and out of the pipe, then I'm dealing with the control volume and system problem. I will like to divide this problem into two portions. One is my control volume, which is fixed, and the other is my fluid that is moving, and I'm calling this a system. So again, another example can be more generalized. We can take a NACA profile, an aerofoil, like let's say I have an aerofoil. This is my aerofoil, and I would like to see the lift and drag that occurs in this aerofoil as the fluid is flowing around this, aerofoil. Okay, so here now I have to fix my control volume. So let's say this is my control volume. Okay, this is my control volume, and by fixing this control volume, it means that now I'm going to study my system, that is my fluid, within this control volume. So the fluid that is flowing over this NACA profile in this control volume, that will be my point of interest, and this is what I'm going to study. So why are we doing this? We are doing this because we want to develop a relation between our control volume. We want to develop a relation between our control volume and our system, that is our portion of fluid that is moving through this control volume. This is an aerodynamics problem, because we use such scenarios to find the lift and drag on an aerofoil, and we study the flow patterns by visual methods and also by simulations to study the flow, the drag coefficient, the lift coefficient of an aerofoil, and how will this behave if it is fixed in an aircraft. So this is simple fluid dynamics problem, but still we divide this problem into two portions. Again, one is our control volume, you heard this term again and again, which is our fixed portion, and the other is the system, that is our moving fluid. So here we are more concerned about the lift and drag coefficient in this particular case. In the pipe example, we were more concerned with the flow inside and outside the pipe. We can take other fluid dynamics problem, like if we say, like in previous lectures, we took a boiler and we studied the temperature field in that boiler. So that for that purpose, we also defined a control volume, and in that system was our flowing fluid that was moving through that control volume. So there are many examples in our practical life that we use to study the aerodynamics or the flow rates or the temperature fields in our daily life. So what we need is a Renault transport theorem. So this theorem provides us with a relation through which we can compute our rate of extensive property as a system moves throughout our control volume. So this theorem provides a relation between our system and our control volume. So if we would like to see what forces is the system subjecting on the control volume, we will use Reynolds transport theorem. If we want to see the behavior of the system if it goes through a control volume in which certain object is placed, so we will use Reynolds transport theorem. So this theorem basically gives us a relation between a system and a control volume, and with this relation we can see the behavior of the system within the control volume, because we again divide our fluid dynamic problems into mainly two portions. One is our system and one is our control volume. Again, system is our fluid and control volume is our fixed geometry, or that portion that we want to specify around our concerned geometry. So again, let's move forward to the next slide, and here I'm going to talk about our extensive and intensive property now. So what are extensive and intensive properties? So extensive properties and intensive properties, you have already covered this in your thermodynamics course. Extensive properties are those properties which are dependent on the amount of a system. Now it is dependent on mass, because this is our quantity of matter. So the amount of the system, it is here. Extensive properties are those that are dependent on mass, and intensive properties are those that are not dependent on mass. So this is the main difference. Why we need these properties? Because extensive properties here is denoted by capital B. These are my extensive properties. Extensive properties. And here extensive properties includes mass, momentum, and kinetic energy. So these are my extensive properties, and these are my intensive properties that are also defined as extensive property per unit mass. So if I take the intensive properties of these extensive properties, I will get these terms. So what I'm more concerned about is extensive properties, and these extensive properties are, in this case, my mass, momentum, and kinetic energy. Because when a fluid moves through a control volume, so the forces that occur due to that flow is due to these extensive properties, that is the mass, momentum, and kinetic energy, coupled with, of course, velocity or acceleration. So these extensive property subject our control volume to different type of forces, and that's what we are concerned about. That's what we want to find, and that's what we are more interested to develop a relation between our system and our control volume, so that we can develop flow scenarios and predict our flow scenarios, that what is going to happen when a certain system flows through a certain control volume. And this is what we are more particularly interested in, that what happens when a fluid flows through a particular object. Flows through means if a flow through a pipe. Let's suppose this is a flow through a pipe. this is an orifice, and I'm more concerned about the flow rate that is occurring in that pipe. So this is what happens when a fluid flows through a particular object. Okay, so here again there are my system, this is my system, and this is my control volume. One is fixed, one is moving, and the other is what effect the fluid will have on a particular object when it interacts with it. That was my aerofoil, that what will happen when an aerofoil is subjected to a fluid, a flowing fluid. What will happen, how much drag and lift will it generate? So these are the 2 points that I want to I will explain again and again over this course of lecture, and this is what I'm more concerned about, that what happens when a fluid flows through a particular object and what happens when a fluid interacts with a particular object. And this is what we gain from our Reynolds transport theorem. So this is what our Reynolds transport theorem gives us. So let's move forward. So we can first develop this relation from our extensive and intensive properties, because to see the relation of our control system and our control volume, we will need this relation, because in this we are studying all our extensive properties that was denoted by B. In the previous slide it was mentioned, that is our mass, our momentum, that is our momentum, and kinetic energy. So these 3 are my extensive properties, and these extensive properties are related by this equation, that is MB, and B was, if you remember, was equal to B over M, that was extensive property per unit mass. So now you can make sense of this equation, that why we have written it like this. So we will use this equation to develop a relation between our control system and our control volume. So if we write this equation for, let's suppose, a small fluid, or a small portion of fluid, or let's say a single particle of fluid. So if the limit delta V is approaching to 0, means we are taking a very small quantity of fluid. So we can write this equation like this. If we use the sigma sign for I number of particles, so this B is for I number of particles, I can be 1, 2, 3. So if we want to see the effect of these extensive properties in a system for a single particle, so I will be then equal to 1. So B is our intensive property, and that is rho for density, and V is for volume. Here we have written this mass in terms of rho V, so you can see that density is equal to mass per unit volume. So mass can be equal to density into volume. So this is what this term represents here. So this is for a single particle of fluid, if I put I is equal to 1, but I want this relation for the whole system. So what will I do is I will integrate this equation for the whole system, and this is what I get. Now I'm integrating this for the whole system, so I will get this extensive property for the whole system in terms of density, intensive property, and volume. I want to see the rate of change with respect to time of these extensive properties in the system. These are my extensive properties in the system. So I want to see the time rate of change in these extensive property of the system. So I will simply use my full derivative d over dt to see the change with respect to time in these extensive properties. So this is for the system. I can write the same equation can be written for the control volume. So this is my relation for the system, that is my moving fluid, and this one is for my control volume, which will be fixed, and my fluid will be moving. So I have written the terminology of the extensive properties. I am using the terminology of extensive property for my system and for my control volume, and I have written these two equations. Now I'll further use these two equations in a particular scenario to develop a relation between my system and control volume for a uniform geometry and a uniform velocity. So let's move forward. Now this is my control volume. This is my control volume, and by control, defining this as a control volume, this will remain fixed, and this is my system. It means this is the fluid that is within this control volume. So you are seeing that they are both coinciding. They are both coinciding. They are both the system is within the control volume in this particular case. So if I say that at a certain time t, both the system and the control volume coincide. Okay, at a certain time t, both the system and the control volume is coinciding. So what this means is the extensor parameter b at time t of the system and both the control volume and system coincide. What will be that equation now? That equation that we written, that b is equal to our m small b. So we want to relate this equation both for our system and our control volume, and we can write this at a certain time t. The extensor property of the system will be the same as the extensor property of the control volume at a certain time t. Why? Because they are both coinciding. The fluid is inside the control volume, so the extensor property of the system will be the same as the extensor property within the control volume. So in this case it is the same because both the control volume and the system are coinciding. Now let's see when a scenario when the system is moving out of this control volume. So what will happen? We will again write this equation, but it will this equation will now change when the system moves out of this control volume. So we will like to see that scenario and develop an equation. So again, that is the equation that we previously saw, that at time t when both the system and the control volume were coinciding, the extensor properties were the same. But now this is again our control volume, and in this scenario at a certain time t plus delta t, this control system is now moving out of this control volume. So this is our this is our control volume, and this is the system that is moving out at a certain time t plus delta t. So because we are dealing with a fluid kinematics problem, so definitely with a change in time this fluid will move out of the system. So now we will write this equation. We will write this equation for this scenario. What happens to this equation when we apply it on this scenario? Here we will have two portions, because in the previous case the system and the control volume are coinciding, but now they are not. So we will have two portions. One is this is 1, this is 2, or if we use the Roman letters that will be good. I will use Roman letters. So this is my portion number 1, portion number 2. So this is what is going into the system, that is into the system, sorry, into the control volume, fluid into the control volume and fluid out of the control volume. So that is the my system going into the control volume and my system going out of the control volume. So I get these two extra regions that I will like to explain it further when I write the equation for this scenario. So now let's see what our equation will look like, and this is how our equation will look like when we write this equation for time t plus delta t. So the extensor property of the system at time t plus delta t will be equal to the extensor properties of the control volume at time t plus delta t minus you can ignore this minus sign for a little while, I will come back to it. That is, this is the extensive property of the fluid going into the system, and this is the extensive property of the fluid going out of the system. This negative sign is used to differentiate the fluid going into the system from the fluid going out of the system. So that negative sign is here for the fluid going into the system, representing the extensive properties of the fluid going into the system. So that B1 is this region and B2 is this region, because this is the extensive properties B1 of fluid going into the system and B2 of my fluid going out of the system. So this negative sign shows that the fluid is going into the system. This positive sign shows that the fluid is going out of the system. So here now again, if we want to see this equation, and let's again go through it. So my extensive property of system at time t plus delta t, at time t plus delta t, when they are not now coinciding, so that extensive property of my system will be equal to my extensive properties of the in the control volume at time t plus delta t minus the extensive properties of the fluid when it is going into the system, and by into the system I have put a negative sign to represent it, the directional sense of it, and B2 is my fluid going out of the system, and for that I have put the positive sign to represent that it is going out of the system. Now what does this mean? Here we are going to talk about the left hand and the right hand side of this equation and explain it a little bit further. So if you can see, I'm more concerned about the extensive properties of the system at this time, and then I'm equating it to other terms. Okay, so let's take this term, that extensive property of my control volume minus the extensive property of my fluid that is going into the system. So this is my control volume. This red dotted, this dotted, this dashed is my control volume. So this term B is my extensive properties in the control volume. Okay, so this is my whole control volume, that red dashed area, and minus B1 t plus delta t, the extensive property of the system going into the control volume, extensive property of the system going into the control volume. So it is representing this region. It is representing this region. This B1 t plus delta t is basically representing this region right here, the extensive properties inside this region of the fluid that is moving into this area. So here again I am subtracting this region, I am subtracting this region from this whole control volume. As you can see the equation, from this whole control volume, if I subtract this region, what will I get? As per equation, what will I get? If I, from this control volume, I subtract this region, I will get this region. I will get this region. Okay, I will get this whole region when I subtract the extensive properties of my control volume and the extensive properties of my fluid that are going into the system. So I get this region plus this region, that is the exit of my control system out of the control volume. So I add this region. So now you can make more sense out of this equation, that why my extensive properties for this whole system is equal to these terms, because by subtracting the extensive properties of the control volume and the extensive properties of the fluid going into the system, we get this region, we get this region. So we got this region, and we now we need to add this region too. So this is our portion going out of the system. So we add this term with this equation, and we get the extensive properties that are going out of the system at time t plus delta t. So now you can make more sense of this equation, that why we are writing it in this term and why we are putting in the minus and the plus signs. So basically what we are more concerned is about the extensive properties of the system that is moving through this controlled volume and moving in and out. So that was our equation for at time t plus delta t, when at time t plus delta t and this fluid is moving out of this system. So this is now how this equation will look like at time t plus delta t. So moving forward, what we are more concerned about is the change with respect to time, because we are dealing with fluid kinematics, and in fluid kinematics the fluid is flowing, and we are more concerned about the geometry of flow, and that geometry of flow is going to change with respect to time. So the change in extensive property with time interval delta t is given below in this form. So what we are more concerned is the total change with respect to time in the system. So this is what this equation become when we see the total change in the extensive properties of the system with respect to time delta t. So we are going to subtract the extensive properties of the system at time t and the extensive properties of the system at time t plus delta t to get the time rate of change of the extensive properties of the system. And again, by system I mean my fluid. I'm going to do the same for my control volume, that is my control volume at time t plus delta t minus my control volume at time t. Then again this term, that is the extensive properties of the fluid going into the system, extensive properties of the fluid going out of the system, and this whole divided by dt, because we are more concerned about the rate because the change with respect to time. So that is why we are using the d by dt for this equation to see the rate of change in these extensive properties with respect to time. So how will this equation look like? We will move to the other slide. So this is what I got from the previous slide. This equation, when I included the time rate of change in these extensive properties, and this is these are those terms that are occupying the volume. So one is my system, okay, so and one is my control volume. There is another difference. I'm talking about the total change with respect to time, so that is why I have written it with capital D over dt. That is what we did when we used this capital D over dt in material derivative, because we were more concerned about the total change, and here we are seeing the total change in the extensive properties of the system with respect to time. We are more concerned about the extensive properties of the system with respect to time when it flows through a particular controlled volume, and those extensive properties, how will they behave when they flow through a particular volume with respect to time. So this is the total derivative of the extensive properties of the system. This is the partial derivative of the extensive properties of that fluid that will behave in that controlled volume with respect to time. So these are the things that occupy a volume, because a controlled volume is definitely a fixed volume and a system is going to flow through that volume. So that is why we are differentiating it in these in volume terms. And then there is the extensive properties of the fluid that is going in and out, that is going in and that is going out. So here we are also taking the mass flow rate in this equation. We are also concerned about the mass flow rate that is going into the system and that is going out of the system. So here we are more concerned about the extensive properties of the fluid going in and out. So there, from this equation can be again simplified into these two terms, one that is occupying the volume and one that is going in and out of the system. So now we can develop a generalized equation for this simple case, for this simple uniform geometry and uniform velocity. But first I'm going to explain this term, that how this A1 V1 got here. How are we talking about in terms of mass flow rate? So let's see this. So let's say this was my equation before I put it in the system. So let's write the equation, that is rho so here that is my equation, that is previously it was written as rho b v, that was my density and that was my intensive property and that was my volume. Okay, so now here I am going to take this volume and write it like this in terms of flow rate. So how I'm going to do this is when I take the I write this volume in terms of area and length. So if I take this, that minus rho b v, and I leave out these two and I write this in terms of area into a certain length, certain delta L. So area into length will give us the volume, and here we are dealing with fluid kinematics, so I can simplify this term further in terms of velocity and time. So that's what I'm going to do, because velocity is our change in length divided by time. Okay, so this is what I'm going to put here, and this is what, so I'll get area into V delta T. Okay, so that is how my AV got here, and that delta T will cancel out with this one. So we will get this term, that is rho A1 V1 B1, when we put this A1 B1 in this. So again we can also write this in terms of mass flow rates. That is what we are more concerned about. That is my mass flow rate into the system, my mass flow rate out of the system, and this is what I'm going to represent it with these extensive properties. Okay, so again this was how I got this equation, and I divided into these terms, and now I'm equating these terms to a more generalized terms. Okay, and that is the total change in my extensive properties with respect to time, that is my partial change in control, the extensive properties within the control volume, the fluid that is within the control volume and its extensive properties, and its change with respect to time, the partial change in respect to time. And this is my fluid going into the system. This is my fluid going into the system, their extensive properties, and my fluid going out of the system and their extensive properties. So before going any further, again I would like to remind you that why we are doing this. We were doing this to develop a relation between our system and our control volume. So for that we took our control volume like this, and through it we passed a system of fluid. So that's how we got these terms, and now I'm going to write this in a generalized form to get a Reynolds transport theorem in a more generalized sense. So this is how my final Reynolds transport theorem will look like. that is my total change in the extensive properties within the system. Okay, total change within the system, and by system again, what is our system? That is our fluid. So the total change with respect to time in the system is equal to the partial change in the extensive properties within the control volume with respect to time, plus the fluid and its extensive properties that is going out of the system, minus the extensive properties of the fluid that are going into the system. So this is the total change of the system, and this total change is equal to the change in the control volume. That is the fixed, that is my fixed geometry here, and the stuff that is crossing the boundaries. Stuff that is crossing the boundaries is again our fluid, but we are more concerned about its flow rate, that when it is going into the control volume and going out of the control volume. So that is how I am relating my system and my control volume, and this is what we are more interested to see, that how our system behaves when it moves into the control volume, but not into the control volume, how it moves out, and how will it behave inside the control volume depending on the control volume, because the control volume can change. Here it is a confined control volume and the fluid is going into the system inside, and the fluid is moving inside this control volume. So our control volume can be again that aerofoil, and the space around this aerofoil can also be designated as a control volume. So what will be this, how will this equation behave in this case? So again we will be more concerned about the extensive properties of the system, but how will those extensive properties behave inside this control volume, and when they go in and when they go out. So this is how I am going to get the total sense of my extensive properties of my system. And again, by extensive properties I mean my mass, my momentum, my kinetic energy, because this is what we talk about. We talk about the conservation of mass, we talk about the conservation of momentum, we talk about the conservation of kinetic energy, and we have already discussed that why we talk about the conservation of mass, because the total mass that moves through the system will remain the same, the total momentum will be conserved, the total energy will be conserved. So that is why we take our extensive properties in terms of mass, momentum and energy. So this is again, let's move to the other slide and let's see what this equation actually represents. So again, this is my Renault transport theorem, and this equation is derived from uniform surfaces and uniform velocities. So this is my simple case, that what I derived earlier, that I derived it for a uniform surface. I took a uniform control volume, and I assume that my velocities are uniform, that are moving through this control volume. So we would like to generalize it more for more complex fluid flow phenomena, that for example, that if we want to check the aerodynamics of a car, or the aerodynamics of an aerofoil, or if we want to see the extensive properties inside a boiler, so we need a more generalized term so that we can apply to every scenario, that how will this Reynolds transport theorem act in that scenario, a more generalized term. So let's take this scenario in which we have now an arbitrary shape. This arbitrary shape, these blue dots are now my control volume. These blue dashes represent my control volume. Okay. So this is my control volume that is fixed, and this is the fluid that is going into the control volume, and that is the fluid going out of this control volume. So now this shape is not uniform, you can see, and the velocity will not be uniform because the shape is not uniform. So now we would like to make an equation so that we can generalize this Reynolds transport theorem equation and generalize it for different flow phenomena. So let's say I take a portion of this outflow. Okay, I take a portion of this outflow and I draw it here. Well, I'm not actually going to draw it, but I'm going to represent it here like this, that I have taken a portion of this outflow and I have magnified it, and I'm now showing it here. So what is happening here? Let's see that. What I'm more concerned about when I talk about generalizing this equation, I'm more concerned about the fluid that is going into and out of this control volume. So I'm generalizing this term. I'm generalizing this term so that I can write one equation for this extensive properties that is going into the system and extensive properties that are going out of the system. I want to write one equation for these terms, and for that I'm taking this arbitrary shape, and now I'm analyzing this outflow here. So if I draw this outflow here, this will look something like this, and here I'm drawing two vectors. One is the n unit vector, this is the n unit vector, that is the normal to this surface, n unit vector that is normal to this surface, normal to this outflow surface. And the other is my velocity. This is in the direction of that flow. This is my velocity. Okay, so this is n unit vector, means its magnitude is equal to 1, so it is even, this is only giving us the sense of direction, nothing else, and this is our velocity. So if we take a dot product, if we take and yes, and we are taking a small area, that is delta A here, and we are drawing these vectors for this small area delta A, that is my unit vector n and my velocity vector v for this small area delta A. So let's say I take a dot product of this v dot and dA. Okay, so what will happen? You can remember from your statics course that this dot product will result in v dot n dA cos of theta. So this v dot n dA cos of theta is telling us something. What is it telling us? It is telling us this, that theta, if it is between 0 and if this theta is equal, if this theta is between 0 and 90 degrees, if this is the scenario, then we will get a result that is positive. We will get a positive result. So that positive will tell us that this is the outflow, that the fluid is going out of the system. So this is what it is telling us, this dot product, that if we take the dot product of this velocity v and this unit vector n, unit vector, normal unit vector, that is normal to the surface, and its result is positive, that it means that it's that this theta is somewhere lies between 0 and 90 degrees, and we are getting a result that is positive. So this is how our flow will look like, and this is our outflow. This is our outflow. So let's see another example of our inflow. What will our inflow look like? That is the portion of the fluid that was going out of this control volume. So we got a positive result from the dot product of the velocity and n unit vector. Now let's see what happens when we see a scenario in which we are representing the inflow portion of the control surface. Now I am taking a surface here and I have magnified it and drawn it here. So again I am taking a small control area, that is my delta A, So I am representing the inflow area, so the unit normal, that is the unit normal, that will now be directed inward, the area, because I am talking about inflow, so that unit normal will be directed inwards. So now the velocity is again in the same direction, that is moving outwards, because the fluid is moving in a particular direction. The direction of the fluid flow is the same, so that will be the direction of our velocity. The velocity direction will not change, but the unit vector normal direction can change. Depends that if you are taking the outflow portion of this control surface or the inflow portion of the control surface. So here you can see the for the outflow portion, this unit normal vector is coming out of this control surface, and for this case, for the inflow surface, that is going into the control surface, because we are talking about the inflow portion. So here now you can see the theta. If we take the dot product of, in this scenario, that V dot N dA, we will get V N dA cos of theta. So here you can see that theta is not less than 90, it is more than 90. So if theta in this case is greater than 90 degree, we will get a negative result. We will get our negative result, that is for this portion. When we talk about the extensive properties of a fluid that is going into the system, so that is why we get this negative sign also. So we get this negative sign because here the theta is greater than 90 degrees. So if we take the cos theta of something that is greater than 90, we will get a number that will have a negative sign with it. So this will represent our portion of a fluid that is going into the controlled volume. So if I'm going to write an equation of this, that is B out minus B in, so I can write it like this, that is B out minus B in is equal to the control surface out. This is how I'm going to represent it. That is the control surface going into the that is the extensive properties of the fluid going out of the system, minus the extensive properties of the fluid going into the system. So here you can see the minus sign due to this dot product, because the theta here is greater than 90. We have already established this. So now we can write this as a single term. Okay, so we can represent these with a single equation, that is rho bv dot n dA. So we can write this single equation for this scenario, for the stuff that is crossing the boundary. We can now write a single equation for this, because here the dot product is now specifying that whether this extensive property is going, this fluid is going into the system or going out of the system. And what are we studying? Either we are studying the extensive properties of the fluid that are going into the system, and either we are studying the extensive property of a fluid that are going out of the system. So this dot product is defining that in and out in inflow and outflow of this fluid. So that is why we can use this single equation, because now we can incorporate both the inflow and the outflow in this single equation. So again, this is how my final Reynolds transport theorem will look like. That is, my total change in the extensive property of the system with respect to time is equal to my partial change in the extensive properties of the fluid that are inside the control volume with respect to time, and the fluid, the system that is going into and out of the system. And now you can see I've simply replaced this term here in this equation by this. So this is our more generalized form of Reynolds transport theorem, and here we have just simplified our flow that is going in and out of the system in terms of using the dot product. So this dot product between these two terms, my velocity and my unit vector normal and the small area, can now define the direction of my fluid, that either it is going in the system or either it is going out of the system. So now this is a more generalized term, and it can be applied to any scenario, not only to uniform surfaces, uniform velocities, but it can now be applied to any scenario. So this is what I wanted to do to generalize this Reynolds transport theorem, into this form. So this is our this is how our final equation for Reynolds transport theorem looks like. So let's again go through what This means why we have done all this, because we were more concerned about a relation between our system and our control volume. So again, our system was our fluid and our control volume was the geometry that is fixed. So what happens when this system interacts with this control volume, or what happens when this system moves through this control volume? We needed a relation that was provided to us by a Reynolds transport theorem. And Reynolds transport theorem begins its arguments by taking the extensor properties for the system and applying those extensor properties when that system is moving through controlled volume. So what will happen when these what will happen to these extensor properties when they move through a control volume? So that control volume can be an internal surface, that can be an external object, and we will be studying the aerodynamics of that object. For an internal case, we'll be studying a flow rate. So it can be anything, but basically what this equation does, it provides us a link between our system and our control volume, and how these extensor properties change with time when it flows through a particular control volume, and what will be the inflow out and outflow that when fluid flows through a controlled volume. So this is what it basically tells us. It provides us a link between our system and our control volume, and how the system behaves when it flows through or around a particular controlled volume. So hopefully this is clear, and see you in the next class. Allah Hafiz.